All right, let's look at the last three indeterminate forms. So 0 to the 0, 1 to the infinity, and infinity to the 0 power. And here's sort of a typical, a fundamental limit, one that's probably worth memorizing. So we want to compute this thing. And if you notice, the limit as x approaches 0 of 1 over x, that limit does not exist, right? From one side it goes to positive infinity, and then from the other side it goes to negative infinity. So, I mean, technically speaking, we want to check 0 from the left and from the right. And so when we do that, now it's not a 1 raised to the does not exist, right? When I check x goes to 0 from the right, this goes to positive infinity, and so this has the form 1 to the positive infinity, which is okay. And then when I check 0 from the left, it has the form 1 to the negative infinity, which is okay. So the two one-sided limits both have a good indeterminate form. They're just a little different. So I'm gonna work this thing from both sides simultaneously and just make use of the fact that we do get the good indeterminate forms from either side. Okay, let's take a look at how to do this problem. Okay, so the first step in evaluating these types of indeterminate forms where you've got an issue with the exponent is remember the logarithmic differentiation technique where we applied the natural log and that took that exponent and wrote it as a multiple, right? Made things much easier to deal with. So we're gonna try the same thing here. So I want to compute this limit, which I'll call L. And so to do that, I'm going to take the natural log of both sides, right? So the natural log of the left-hand side is equal to the natural log of the right-hand side. And now remember, the natural log function is continuous. And so that means I'm allowed to switch the natural log function and the limit operation, right? So the log of the limit is the same thing as the limit of the log. And so right now this is the limit as x approaches 0 of natural log of 1 plus x to the 1 over x. That's equal to the natural log of L. And that's good now because remember our rule of logarithm says that the natural log of a to the b is the same thing as b times natural log of a. So I can write this 1 over x down in the front. And so this limit now is equal to the limit as x approaches 0 of natural log of 1 plus x, right? So to multiply by 1 over x is the same thing as to divide by x. So that's equal to the natural log of L. And now, if you look, this thing has the good form 0 over 0, and now that means we're allowed to apply L'Hopital's rule. And so that'll be the last couple steps. Okay, so if we call our original limit L, then that means the limit as x approaches 0 of natural log of 1 plus x over x is equal to the natural log of L. We got that just by taking the natural log of both sides of this thing and then switching the limit and the log operations. So now we do get the good form 0 over 0. Just make sure you double check that. That means L'Hopital's rule does apply. And so I will take the derivative of the numerator. So the derivative of natural log of 1 plus x, it's the derivative of the thing in the parentheses, which is just a 1, and then divide by the thing in the parentheses, so 1 over 1 plus x. And then in the denominator, the derivative of x is just a 1. So we got that this limit is the same thing as this limit, and all the while it's called natural log of L. So now we can certainly plug 0 in everywhere we see an x. And so when I plug in 0 into this thing, I just get a 1. So now I know that 1 is equal to the natural log of L. And so now I can slap an e underneath both sides. In other words, exponentiate both sides. So that says that e to the 1 is equal to e to the natural log of L. And so e and natural log are inverses of each other, so they cancel. That says that L is just equal to E. So my final answer is just that Euler's constant or the number E. So that would be a good final answer. right? So in some analysis books, this is the way people define the number e, right? It's the limit of this thing, whatever that happens to be. All right, here's another example where we've got an indeterminate form involving the exponent. So we want to look at the limit as x approaches 0 from the right of tangent of 2x, all raised to the 3x power. So if you plug in 0, you get, right, tangent of 0 is 0, and then in the exponent we get a 0. So this has the form 0 to the 0 power. So we want to try to rewrite this thing. Again, anytime there's a moving exponent, take the natural log of both sides. That's always step number one. So I'm going to call this limit L. When I take the natural log of both sides, I get the log of the limit of the thing is equal to the natural log of L. Because natural log is continuous, I'm allowed to switch these two things. In other words, the log of the limit is the same thing as the limit of the log. And just carry out the right-hand side. And so now the reason that we did that is so that, right, we know that the log of a to the b is the same thing as b times natural log of a. So I can take this 3x and write it down in front. And so now I've got the limit as x approaches 0 of 3x times the natural log of tangent of 2x. And so this thing has the form 0. And then natural log of 0, well, this thing goes to negative infinity. So now this thing has the form 0 times negative infinity. So we still have the good indeterminate form. But now that means I should take this thing, right, take one of the factors and write it in the denominator. So flip it and write it in the denominator. So to multiply by 3x is the same thing as to divide by 1 over 3x. And so these two limits now say the same thing. And now if you look at as x goes to infinity, right, tangent of 0 is 0, and natural log goes to negative infinity. So we get a negative infinity in the numerator, and then as x goes to 0 from the right, I get a positive infinity in the denominator. So now I've returned to one of the two good indeterminate forms. Now I can apply L'Hopital's rule. So now we want to apply L'Hopital's rule to this thing and see if we can get a good final answer. Okay, so we have taken this limit and we've rewritten it as a fraction involving a natural log. So the limit as x approaches 0 from the right of tangent of 2x raised to the 3x power. If I call that L, then that means the limit as x approaches 0 from the right of natural log of tangent of 2x over 1 over 3x is equal to the natural log of L. And so now I can take the derivative of the numerator and denominator, right? So we checked that this thing had the good indeterminate form, negative infinity over infinity, so we can apply L'Hopital's rule. So the derivative of the numerator says take the derivative of the thing in the parentheses, so that's 2 times secant squared of 2x using the chain rule, and then divide by the thing in the parentheses, so now divide by tangent of 2x. And now the derivative of 1 over 3x, it's just negative 1 over 3x squared. So now you can rewrite all of this mess, right? So just flip the bottom and multiply by the top. So we get the limit as x approaches 0 of negative 6x squared secant squared 2x over tangent of 2x. And so let me factor this thing in such a way that I get some familiar limits. So we know how to deal with x over tangent of 2x. You've either memorized by now that this thing is 1/2, or you can apply L'Hopital's rule to see that you get 1/2 as x goes to 0, right? That followed from the old sine x over x limit. And you can check that the limit as x approaches 0 of sine x over x is just 1 by using L'Hopital's rule, right? So now we've got a thing that we can plug in 0, and we've got a thing where we've memorized the limit, or we can just use L'Hopital's rule again. And so the limit as x approaches 0 of this thing, right? So the first piece, that's just 0 times 1, which is 0. And then the limit as x approaches 0 of the second piece, that's 1/2. And so this tells me that the natural log of L now is equal to 0 times 1/2. So let me write that up here, right? So this limit, right, it's just 0 times, right, 0 times 1/2. And so we know that's equal to the natural log of L. By the way, right, what's L'Hopital's rule say for this thing? Well, it's 1/2 secant squared of 2x. And then if you plug 0 into this thing, you just get 1/2. So that's another way to see that this thing is equal to 1/2. So now I know that 0 is equal to natural log of L. So what's L have to be? Well, if I exponentiate both sides like I did in the last example, that tells me that L should be equal to 1. So I know that 0 is equal to natural log of L. That tells me that e to the 0 is equal to e to the natural log of L. These two things cancel, and so I'm left with 1 is equal to L. So that's my final answer, right? Now I know that the limit as x approaches 0 of tangent of 2x raised to the 3x power, that's just going to be a 1.